Okay, so this is a course of algebraic geometry. So I'll give some very brief introduction and then we start right away. So in algebraic geometry, we will study what one would call algebraic sets and algebraic varieties. Which are just zero sets of systems of polynomial equations. And this is a little bit like generalization of linear algebra, but it's much more subtle. So in several variables. So just we have so f1 of x1 to xn is equal to so on fn of x1 xn in k is equal to 0. So we study this zero sets in k to the n, where k is a field. So, for instance, to have something more familiar, if we look at the equation x squared plus y squared is equal to 1, then at least if we are working over the real numbers, so if our field k is the real numbers, then this gives us in R2, this gives us the unit circle. No? This is 0 set. So this is standard thing. Okay. If also in R2 we would instead look at x squared plus y squared equal to minus 1, in R2, this would be the empty set. And actually this shows already some of the problems. These two equations are very similar, but the solutions are very different. And this has to do with the fact that our field R is not algebraically closed. So we get many case distinctions if the field is not algebraically closed, which is why we will assume in the whole course that our field K is algebraically closed. So these are much easier to study. If K is algebraically closed. So you can usually assume, and so we will assume that and if you wish, you can assume that our field is the complex numbers. Okay. So in this case, if we work over the complex numbers, this algebraic geometry is closely related differential geometry. And complex analysis. We will not get to this, but there are, and so some of the more advanced tools of algebraic geometry actually, are based on complex analysis, function analysis, and differential geometry. But we do the elementary algebraic theory, so therefore we will not come to that. We could also, if our field is like the rational numbers, then we come to arithmetic algebraic geometry. So where one is, for instance, interested in the solutions of polynomial equations in rational numbers. And that's a a very different problem. So this is part of number theory. So basically, if one does want to study such problems, so for instance, the typical question, so we have, for instance, Fermat's theorem. If we take the equation x to the n plus y to the n is equal to z to the n, or with n bigger equal to 3, then this has no solutions. In Q without 0 to 3. So there are no solutions where not one of the variables is 0. So this would be an equation. Okay. So this would be, so here you have okay. So this is, obviously you have heard about this, one of the most famous problems, which was solved maybe a little bit more than, I don't know, maybe 20 years ago or something, to prove that this is indeed the case. As you can see here that to study this space over the complex numbers is quite simple, but if you instead are interested in rational solutions, it becomes incredibly difficult. So kind of the questions which are easy over the complex, so the questions you want to study in arithmetic algebraic geometry are questions that in complex geometry would be trivial, but they are, you can barely study them, whereas in complex geometry or in over an algebraically closed field, you study more difficult problems, problems which are geometrically more difficult, but they are, on the other hand, working over a closed field makes them much simpler. Okay. So, as I said, in this course we will assume that our fields are right here. So now let me try to start. First I want to briefly talk about polynomials so that we are on the same page. In our algebra course we basically talked about polynomials in one variable, but polynomials in more variables are not more difficult, so let me just review them. So for me, as we had it in the algebra course, when I say a ring, means for me a commutative ring with 1. Because I don't consider other rings. So we denote Rx, polynomial ring with the ring of polynomials with coefficients in R. assuming you remember it, it's the obvious thing. So some aix to the I, so elements are some aix to the I, A are elements of R, and then they are added and multiplied and so on in the usual way. And so now the polynomial ring in several levels. So we define R of x1 to xn to be, we take the polynomial ring in one variable s, and this is our coefficients, and we take polynomials in the last variable with coefficients like this. This is the polynomial ring in n variables. So inductively we have defined it for any number of variables. Okay? And so this then also turns out to be the obvious thing. It's easy to see that so an element, so polynomials, so f in R x1 xn can be written as f equals sum over some indices I1 to n bigger equal to 0, finite sum a I1 to in x1 to I1 times and so on to in, where only finitely many of the ai are 0. So with so where a and 1 and 1 n are elements in R and only finitely many non-zero. Okay, so this is as we are. I mean, I expect you anyway know what the polynomial is. It is the obvious. So this would be polynomial, and we want to introduce a couple of more words about them, and then we use them. So I call these expressions x1 to the I1, xn to the in are called monomials. And this degree of this thing of this monomial is the sum of the powers here and if I have polynomial, the degree of the polynomial is the degree of the highest degree of a monomial whose coefficient is non-zero. This f is the largest degree of a monomial x1 to the I1 xn to the in with the corresponding coefficient, so the number in front of it is called coefficient, whose coefficient a I1 in is non-zero. We'll see later when we look at projective varieties. We will be particularly interested in homogeneous polynomials, which are polynomials such that all the so that all the monomials with non-zero coefficients have the same degree. So f is called homogeneous, of degree D if all monomials of F with non-zero coefficient have degree D. Okay, so I haven't told you anything, I've just introduced these words. So now we want to start talking about. It's just that we now have some of the words that we want to use. So now I will introduce algebraic sets and algebraic varieties. So let me talk about algebraic sets. So affine algebraic sets. So we first, well, maybe I first say. So we will first study affine algebraic sets, which are certain subsets given by solutions of polynomials in k to the n. And these are some nice sets, but it actually, for many purposes, is nicer to have sets which so algebraic sets which in a suitable sense are compact. For this, we will later introduce projective algebraic sets. So we introduce projective space, and inside this, we take the zero sets of homogeneous polynomials, which are projective algebraic sets and projective varieties. But these we will start later. In this first chapter, we talk about the affine algebraic sets. And so we want to study affine algebraic sets. So, and we will introduce also some. We'll also introduce. So we'll introduce some interesting concepts. So one is a risky topology. Maybe I should try it again. Which is a topology on, say, k to the n, whose closed subsets are these affine algebraic sets that we introduce. And then we will also introduce the irreducible components. Which is, if you have an affine algebraic set, so say the zero set of some polynomials, then it might be that you can write it as a union of two smaller algebraic sets. And the claim is that any algebraic sets can be written as a union of finitely many smaller algebraic sets, so that these cannot be further decomposed. And these are the irreducible components. So just a picture, if you take the zero set of x times y, so if x and y are the coordinates on A2, then this will look like that. And you can imagine that the irreducible components are the x-axis and the y-axis. But we will see that later, in the moment I just introduced it. So, okay, now we start. So, as I told you, in the whole course, K is an algebraically closed field. Now we want to say, first I say what affine space is. So this is a bit of an anticlimax. So affine space, or n-dimensional affine space, An, so is just, it's denoted An and this is just k to the n. So which is the set of all a1 to an with ai elements in k. Okay, so this seems maybe a bit nonsensical to give a different name to k to the n, but that is, that's the standard usage in algebraic geometry. This space, k to the n, is called n-dimensional affine space and denoted an. Okay, so that's what it is. And so, now if we have a polynomial, f in is when n variables x1 to xn defines us a function on an. Which are obviously also denoted by f. So from an to k, namely, so what is, so if p is equal to a1 to an is a point in an, we have f of p is defined to be f of a1 to an. In other words, we just replace the variables by the coordinates of the point and the variable. Okay, that's the obvious way how this defines a function. Okay, so obviously, so this is a nice function. We can talk about the zero set. So the zero set of f is obviously, so we give a name to it, is c of f, which is obviously the set of all points p in an such that f of p is equal to 0. Not a big mystery here. And now we will be interested in solutions of polynomial equations, which we can always write as zero sets of polynomials or sets of polynomials. So therefore, if S is a set of polynomials, we can define its zero set is just z of S equal to the set of all points in an such that f of p is equal to 0 for all polynomials. Or if you wish, you could also write this as intersection all over f in S is 0 set. Okay, so this is the zero set of a set of polynomials, and in the final algebraic set is just any set of this form, any subset of an of this form. So subsets of the form 0 in an are called affine algebraic sets. Okay. So that's this definition. And now, this is what we want to study. We want to study such zero sets. So let's look at some simple examples. What kind of things can happen? For instance, if we take the whole of an, this is either, I can take it as a zero set of the constant polynomial 0, no, that vanishes everywhere, or as the zero set of the set, of the empty set of polynomials. Because now obviously, if the set is empty, there's no requirement. Okay, so that's one example of an affine algebraic set. And the same way, if you take the empty set, this I can take either as a zero set of the constant polynomial 1, or I can take it as a zero set of the whole polynomial. Because obviously there's no 1 is a polynomial, so it vanishes nowhere. Okay, and as 1 is lying in here, obviously is also present. Okay, so these are some trivial examples. Then if we take a point in AN, this is also an affine algebraic set. So point P, so it has some coordinates A1 to AN. This is an affine algebraic set because this is equal, I mean, strictly speaking, if I take P, this is the zero set of x1 minus a1 until xn minus a. Because this precisely says that the ith coordinate of the point has to be ai, which means that the point has to be this one. Okay, so points are also affine algebraic sets. And we can look at, for instance, if we take the zero set of y minus x squared, this would be a conic. So if I make drawings, I make them for the real numbers because I cannot this is supposed to be in A2. If I was supposed to draw this over the complex numbers, I would have to draw something two-dimensional inside something four-dimensional. I don't quite know how to fit that on the blackboard. But over the real numbers, this just is the usual conic, so it will, the coordinate axis, it will somehow look like this. So it's a parabola. Can look at some other such examples. For instance, if I look at the zero set of y squared minus x times x minus 1 times x plus 1, then how will this look like? So the square of this, again, let's look over the real numbers. So the square of the y coordinate must be equal to this product. So if any of these is 0, then the square is forced to be 0. So we know that over these points, so minus 1, 0, and 1, it has to go to this point, and the real points will look somehow like this. So this would be a non-singular cubic. You can also look at another case. So this is y squared minus x to the 3. Then the same kind of argument will tell us that it will look like this, where this is the origin. This would be a cuspidal cubic. Okay, so there's some difference here. This is what one would call non-singular, so that means it's actually a manifold. If one works, if one views it over the complex numbers, it's would be two-dimensional real manifold or one-dimensional complex manifold, this thing. Whereas here you have a singularity. There's a point where it's not a manifold. But this we will deal with later. And I will just call, if f is a polynomial, so x1, xn is a non-constant polynomial, surface. Okay, so now let's move to the next step. So we have, so this is algebraic geometry, which maybe has to do with the fact that we take the zero sets of polynomials, but obviously if it's supposed to be algebraic geometry, we are supposed to be able to use algebra to study our affine algebraic sets. And the first step to do this is to see that affine algebraic sets are not just zero sets of any set of polynomials, but we can choose them as zero sets of ideals in kx1 to xn, so that we can study them via studying these ideals. Okay? So to see, and every affine algebraic set is the zero set of an ideal in kx1 to xn. So this is at least we have okay, so let me now see. This is actually quite obvious if you think of it. Maybe even you could figure out why in a moment's talk. I mean, with a little I told you. I mean, because the idea is that the zero set of a set of polynomials is the same as the zero set of the ideal generated by that set. Okay, so for S in x1 xn, we denote S, the ideal generated by S, the set, that is as usual, set of all linear combinations AI f to the I, where AI is any polynomial. So maybe I should say this sum is finite, L is any positive number. The AI are polynomials, and the Fi are the Fi, and the Fi are elements of it. So this is the idea generated by S. As usual, this is the smallest ideal in kx1 to xn, which contains S. So, and we will want to see, and I mean it's actually quite obvious, we have the following lemma. So first, say if S and T are some sets of polynomials. The first thing is something that should be clear is that if S is contained in T, then the zero set of S contains the zero set of T. I mean, the point is, the zero set is of S is the set of all points in AN where all elements of S vanish. So if S is contained in T, then then S imposes less condition on the zero set than T. Therefore, clearly, the zero set of S contains the zero set of T. So this is clear. And the second one is that the zero set of any such set of polynomials is equal to the zero set of the ideal generated by S. Okay. And that is also quite obvious, but let's just do it. Well, we know that the zero set of the ideal generated by S is contained in the zero set of S, because we just proved this, namely because S is contained in the ideal generated by S. Okay, so that's clear. Now we have to show the other inclusion. So conversely, let P be an element in the zero set of S. We have to show it's also contained in the zero set of the ideal generated by S. So let G be any element in the ideal generated by S, so we can write it as sum I, AI, Fi in the ideal generated by S, so it means the Fi are elements in S. So what do we get? If we compute G of P, this is just the sum over all I, AI of P times Fi of P. But as P is in the zero set of S, F of P is equal to 0. So this is it. And so does P is in the zero set of the ideal generated by S. Okay, so it's quite simple. Okay, now I want to introduce this Zariski topology that I talked about. So, which is a topology on the end to begin with, whose closed subsets are the affine algebraic sets. So to set this up, so this is after Oskar Zariski, an Italian mathematician of Polish origin, who was working, I think, in the first half of the 20th century in, I think, in Rome, or anyway in Italy. And then later he went to US, and anyway he's one of the founders of modern algebraic geometry, maybe not of the most modern, but I mean, part of it is that so there was this Italian school of algebraic geometry, which was quite famous. He was in some sense part of it, which they proved all these wonderful results, but they didn't have proper foundations, and so they proved many correct theorems and many not so correct theorems, and it was difficult to distinguish between them, and he was one of the people who kind of overcame this and really made foundations for algebraic geometry so that one could decide whether a proof was correct or not. Okay? In particular, put it on more algebraic basis. But anyway, the Zariski topology is a rather small thing in this context. So, so this is, as I said, the affine algebraic sets are the closed subsets of a topology on AN. Now, and this turns out to be a very convenient language. So you can talk about closed sets, open sets, continuous functions, and all that, using this topology. But one should keep in mind that, we'll see later that this is a very strange topology. The open subsets are very big, the closed subsets are very small, it's extremely far from being Hausdorff, and we don't really do any topology. Mostly we use this as a nice language. I mean, it's not like we do some arguments in set theoretic topology with this thing. Well, there's a little bit, but it's not so much the point. It's mostly to have a nice language. But you have some topology which is very closely related to the algebra, and this is the Zariski topology. So first, to make sense of this, we have to see. I prove a little proposition which will show that whatever I want to define, that this will be a topology. So first, if S alpha is a family of subsets of kx1 to xn, so the wish is a set of sets of polynomials, then if I take the intersection over all alpha of the zero set of S alpha, this is the same as the zero set of the union over all alpha of the zero set of S alpha. Okay, this first statement. So, okay, maybe I can prove it, it's so obvious. So this is basically trivial, it's just something about quantifying, it's just a definition.
The union over S alpha or the zero set of
what? Yeah, no, certainly this, I meant this other thing wouldn't make sense. Thank you. Okay, so why is that? Well, P is an element in this intersection over all alpha the zero set of S alpha, if and only if, by definition, we have that f of p is equal to 0 for all f in S alpha for all alpha. That's what it says. But this is the same as saying that f of p is equal to 0 for all f in the union over all alpha S alpha. It's just the same thing. And so P is in C of the union over alpha S of f. Okay? So this is a triviality, not just a misstatement of the second one is not much more difficult. Namely, if we take two sets of polynomials S and T in K, then if I take the union, I can write this as the zero set of what I would denote S times T, where S times T is defined to be the set of all products F times G with one element from here and one from here. Okay? So obviously, if this is a set of polynomials and this set of polynomials, this is also a set of polynomials, and I claim the union of the zero sets is equal to the zero set of the product. What?
F and S and G in T.
What? Yeah, that's T. Yeah. I mean, okay. Yeah, misprints are kind of standard. I mean, obviously I do them on purpose so that I notice whether you are awake. But okay, thank you. Okay, so let's see. So we want to prove this. is also quite simple. So first we have to show two things are equal, so we show both inclusions. So let P in C of S union C of P, and let so F in element in S and G element in T. So then, it follows that F of P is equal to 0 or G of P is equal to 0. Because so P must be either in Z of S or in Z of T. So if it's in Z of S, then F of P is equal to 0 for all F and S, in particular from this thing, and the other case you get the other. Okay, and so thus, if I take F times G of P, this is just F of P times G of P. That's how quantification in polynomial rings is defined, and it does that, so this is equal to 0. Okay, and so this is this direction, and now the other one. Let's take P in the 0 set of S times T. And assume that P is not in the 0 set of S. We are supposed to show that P is either in the 0 set of S or in that of T. So if it's not in the 0 set of S, we have to show it's in the 0 set of T. So it's not in the 0 set of S, so we can choose a polynomial f in S with f of t different from 0. And now take any g in T, then f times g is in St, so thus f times g of p is equal to 0. But obviously this is equal to f of p times g of p, and this is non-zero. So, as we are, we should have said, but it's clear that if we have a polynomial ring also many variables with coefficients in a field, then it has no, anyway, we are in a field here, so they certainly don't have zero divisors, and so if this factor is not zero, then the other factor is zero. And so we see that P is in the zero set of T. Okay, so these are all rather clean things, so we see this. But what it means is, right, well, I hope you just write it here. So thus, arbitrary arbitrary intersections and finite unions of affine algebraic sets are affine algebraic sets. But here we have an arbitrary intersection of affine algebraic sets, which is an affine algebraic set. For any affine algebraic set can be written as Z of S alpha for some S alpha, and so we take an arbitrary intersection of them. It's again an affine algebraic set. And here the second says the union of any two algebraic sets two algebraic sets is an algebraic set. And obviously, by trivial induction, if it's true for the union of two, then it's true for any finite union. And so this is fine. And so this tells us that the affine algebraic sets form the closed subsets of the topology on A. So let me spell this out. No, maybe you should remember that we showed before that the empty set is an affine algebraic set. And the N is also an affine algebraic set. And these things together, if the empty set is an affine algebraic set, the whole space is an algebraic set, an arbitrary intersection of algebraic sets is an algebraic set, and finite unions of algebraic sets are algebraic sets. This means these are the closed subsets of the topology. But I will spell it out. So this is the following reminder, although you had it in your topology course, which is not so long ago. So the topology on a set X is a collection of subsets which would be called the closed subsets and called open. Such that we have the axioms. First, the empty set and X are open. Second, in a finite intersection of open subsets is open. And third, arbitrary union of open subsets is open. So X with such a topology is called topological space. And in particular, in this case, if we have open subsets, we can talk also about closed subsets. So in this case, so a subset, say A in X, is called closed. If and only if the complement is open. And now, obviously, by just going to the complement, you can make also a set of axioms for closed subsets of topology, which are just the obvious thing. So we have equivalent axioms for closed subsets. So we have that first the empty set and X are closed as a complement, so X is a complement of the empty set and vice versa. Second, finite unions of closed subsets are closed as a complement of finite intersections of open subsets, and third, arbitrary intersections. so obviously, once you have the closed subset, you can again recover the open subset as the complement. So, so we see, when we put this together, that the affine algebraic set is precisely what is written here. The affine algebraic sets form the closed subsets of a topology on AN. And this is called the Zariski topology. So maybe I can briefly just introduce a few more words so that we have them. So, so if again I go back to the case that X is a topological space, and if Y subset X is a subset, so the closure of Y is the intersection of all closed subsets which contain Y. Okay, so that's the closure. And I mean, we say that Y is dense in S, Y is dense in X. If so, the closure, I call it Y bar, if Y bar is equal to the whole of X, so its closure is equal to X. Well, okay, so maybe I don't need that now, but we say that if I have f from X to Y is a map between topological spaces, then f is called continuous. All these things you know, but I want to have them on something like that. If the inverse image of any open subset is open. Is open in X for all open subsets U subset X, and obviously by taking to the complement, and that's maybe more interesting for us for in the moment, this is equivalent to f to the minus 1 A is closed in X for all closed subsets. A in 1. See what else did I want. And we also want to induce topology. So if Y subset X is a subset, the induced topology or subspace topology has as open subsets precisely the intersection of Y with an open subset of X. open. Or again, equivalently, the closed subsets are the intersections of Y with the closed subsets of X. X closed. Okay, so going back, so now we can rewrite this definition already wrote this definition. The risky topology on the N is the topology whose closed subsets are the affine algebraic sets. Closed subsets are the affine algebraic sets. We want to use this to also define the corresponding topology on the affine algebraic sets. Namely, we endow the affine algebraic sets with the induced or subspace topology. And then we can as well do this for any subset of N. So if X in the N is a subset, usually an affine algebraic set, we give it the induced topology. And we call this a risky topology, and this gives this is the risky topology on X. Just a remark. So first, if X is an affine algebraic set, then the risky topology can also be described in a simpler way. Namely, we can say the closed subset of X are the affine algebraic sets which are contained in X. So if X in N is an affine algebraic set, so the closed subsets are the affine algebraic sets. Of AN, Y contained in X. And this is just because, so according to, by definition, X carries the induced topology, so the closed subsets of X should be the intersections of X with the closed subsets of AN. But that would mean we have the intersection of two closed subsets, so the intersection of two affine algebraic sets. We know that the intersection of two affine algebraic sets is again an affine algebraic set. And so that's it. Okay, one can also note, that's one of the reasons why this is a useful notion for us. You can easily check if F in we can't check it yet. I will say it later. I haven't told you everything you need. But first I have to make another remark. Namely, I need this example. So, first one is that, we have to at least have some idea how many open and closed subsets there are. You can imagine that there will be not so many because, zero sets of polynomials are kind of, as compared, if you have the usual topology, you cannot have like an open ball or something like that as a zero set of polynomial. So, but let's at least see a little bit. So, all finite subsets of AN are affine algebraic sets. This is because we have seen that points in AN are affine algebraic sets, and a finite set is a finite union of points. So, and in particular, for instance, if we just look at the case of A1, this actually gives us the topology. So the closed subsets of AN, of A1, are the empty set A1 and the finite subset. So that the open subset would just be, again, the empty set A1 and the complement of finite subsets. I think you have given a name to such topology. How was it called? What?
Finite complement.
Finite complement. I know, the opposite of discrete. As far from discrete as possible. So the finite complement topology. Okay. So in the case of what?
The second one is not finite. I mean, finite complement topology is different, but.
So these are the closed subsets. The open subsets are precisely the complement. This is the finite complement topology. So this one is obvious. The second one, let me give a sketch. Although it's kind of obvious. So let S in the X be a subset. We want to look at the zero set in a finite algebraic set. So if S is the empty set, or S only consists of 0, then the zero set of S is the whole of A1. And otherwise, we have one non-zero element in S. Otherwise, let F be an element of X. Then, for instance, I mean, one doesn't really need this, but for coinference's use, we are over an algebraic closed field. So if we take the zero set of F, so we can write F product, so X minus A1 to the N1 times X minus AN AL to the NL. So split it into linear factors like this, because we're over an algebraic close. So then the zero set of F is equal to A1 to L, which is a finite set. And F is an element of S, so the zero set of S is contained in the zero set of F. Okay, so we see that this set is finite. Okay, so we see, in particular in the case of A1, we see that this topology is very far from being Hausdorff, because we have the finite complement topology. The open subsets are very big, the open subsets are very small, they're just points. Now, if one is not in A1, you don't have the finite complement topology, but it's still true. You can somehow imagine that the zero set of polynomial really is somehow smaller, has a kind of smaller dimension than AN in a suitable sense. So the closed subsets are very small, open subsets are very big. So the topology will never be Hausdorff, and is quite far away from it. And it's not, one cannot do very many topological arguments with it because topology is quite strange. Okay, but that's on the other hand, one can maybe notice following remark. So if we identify, so this is remark, and identify say K with A1 and with a heuristic topology, then polynomials are continuous. So in that sense, and in some, what it turns out that this is the, so this is an easy exercise to see that. It follows more or less from the definition. In fact, the heuristic topology will be the closest topology for which polynomials are continuous. But we don't need that, I just wanted to mention.
Both AN and A1 are taken in the heuristic topology, right?
Yeah, that's what I was saying. Yeah. Anyway, this is, if you want more than a remark, it's called an exercise. Because I'm not going to explain why it's true. It's easy, but not detailed. Okay. I'm a bit slower than I thought. So I want to very briefly, we don't use it now, but we will need it a lot in the future. I want to introduce the idea of an algebraic set. So we know that an affine algebraic set is a zero set of an ideal in kx1 to xn. But there would be many ideals of which have the same zero set, and there's one which is the best, which is what one calls the ideal of this algebraic set. Namely, it consists of all polynomials which are zero on the set. So the ideal, so definition, but now I can also do it first for any subset. X in An is a subset the ideal of X is Ix, denoted Ix is just the set of all f in K x1 to xn which vanish on the whole of X. So which you could say f of p is equal to 0 for all in X. So in particular, so we will mostly be interested in the case that X is itself an affine algebraic set. So then largest ideal in K x1 to xn with, so I call this I, such that the zero set of I is equal to x. No, you can, yeah, it's kind of clear from the definition. So certainly, maybe I will not, I leave this for the moment as an exercise. I think later I will anyway prove this statement. But so what I want to, but we can see we have an ideal canonically associated to an affine algebraic set, because this is completely, you know, once we have x, we know what Ix is. It's kind of given to us once and for all, and so we will see that the algebraic properties of Ix reflect the geometric properties of X. So once we are given, with X we are given Ix, so they are very closely tied together, and so you can expect that the algebra of this ideal will kind of say us a lot about the geometry of X. Okay, we will see this soon, but now I only need to introduce it. And the next thing I wanted to talk about is our first theorem. So I will not get to it, but I can start setting it up. So the first theorem is the Hilbert basis theorem. So to begin with, it's a very simple question, again related to our algebraic sets. We know, so by definition, an affine algebraic set is a set of the form Z of S for S is subset, so a set of polynomials. So obviously this could be a very big subset, very big set of polynomials, certainly an infinite set of polynomials. So we want to see, that's our first motivation, that we can always choose S to be finite. So every affine algebraic set is a common zero set of finitely many polynomials. This is the zero set. Finitely many polynomials. Okay. So that somehow it's not such a huge infinite thing, but for each affine algebraic set we need only finitely many polynomials. And this actually turns out to have geometric property consequences. We will find out that from this fact, or from how we prove it, it follows the statement I talked about before about irreducible components, that every affine algebraic set can be decomposed into finitely many smaller affine algebraic sets which cannot be further decomposed. So the decomposition into irreducible components. I will explain next time what I mean by that. So first let's see this. It's a consequence of an algebraic fact. So first we introduce some algebra. So So this is the following lemma definition. I think that's about as far as I get. So let R be a ring. Remember, that means commutative with 1. So the following are equivalent. First, so it's a certain finiteness property for a ring. First, every ideal I in R is finitely generated. So that means it's written as the ideal generated by finitely many polynomials, by finitely many elements. That means you can write I equal to, say, F1 to FR for finitely many Fi for Fi some elements in I. So it's the ideal generated by finitely many elements. And the second statement is, if I have a kind of a chain of ideals, always one contained in the other, always getting bigger, then this cannot be an infinite chain. After finitely many steps, all the ideals have to be equal. So R satisfies descending chain condition. So that means every infinite chain, so we have I1 containing I2 containing I3 and so on, of ideals in R becomes stationary. So this is how one calls it. So by which I mean there is an n such that for all n prime bigger than n, you get the same. So that means there exists an n such that In is equal to In plus 1 is equal to In plus 2 and so on. So after finitely many steps, all the ideals have to be the same. You cannot make an ideal bigger infinitely many times. Okay. So, and the ring with this property is called unitarian. So, the ring with these properties is called unitarian. So somehow it means also that ideals in rings cannot be arbitrarily complicated, because you have can always generate them by finitely many elements, and if we will show that kx1 to xn is Noetherian, which somehow means that the finite algebraic sets cannot be arbitrarily complicated. You can always describe them in terms of finite amount of data, and so therefore also the kind of properties that they have cannot be arbitrarily complicated. And that's somehow very important, otherwise algebraic geometry would not work. And so now I should prove that these are equivalent, and then I stop. So let's take a chain, so we assume one, and we take a chain of ideals. chain of ideals. And now we take what?
Take the union.
What?
Take the union.
Yes, so I follow the advice from of the regie, so I take the union. So it's easy to see that this is an ideal. Because, to be an ideal means that the sum of any two elements lies in it. But if I have two elements, one will lie in one of them, the other one will lie in another. So both of them lie in the later ones, and I can take the sum there. And in the same way, the product of any element with an element of R should lie there. But if as this is an ideal, this will even happen in the same ideal. So this is certainly an ideal in R. And so therefore, it is finitely generated. Can write I is equal to F1 Fl for some elements. But so I is the union over all of these. So each of these elements must lie in one of them. So so each Fi lies in some I of Ni. And if I just take the maximum of these, so thus if n is equal to the maximum over all I of the Ni, meaning over all this I from 1 to L, then we have that F1 to Fl are all in In. And so, therefore, obviously, In already is equal to I. And so, in particular, we have that In is equal to In plus 1. And so on. Okay? So this is one direction. The other direction, I think, is about less difficult. So from 2 to 1. So let I now make contraposition to assume that I in I is an ideal which is not finitely generated. If such an ideal exists, we have to be able to find an infinite chain of ideals which does not become stationary. So let F0 be an element in I. Why not? And F1 an element in I without, say, the ideal generated by F0. And so inductively, we take Fn plus 1 to be an element in I which does not belong to the ideal generated by F0 to Fn. And notice that I can never be equal to this ideal, because if it was, I would be finitely generated. So we can do this ad infinitum, and then clearly we have that the ideal generated by F0 is contained in the ideal generated by F0 and F1, and in fact they are different, and because we always take an element which does not lie in before, and so this is an infinite chain which does not become stationary. not. What? I will take, no, so I choose, maybe I wrote it back. I choose an F1 which does not lie in this idea. Okay? Then I choose an F2 which doesn't, sorry, I misprinted it. So I kind of misread what I wrote. Okay? You're right. So I take F1 to be in the ideal minus F0, the ideal general F0. I somehow, got confused, but because I didn't want it to be in this, and so anyway, but it's, and so I negated it twice. So Fn plus 1 is in the ideal, but not in the ideal general alpha 0 to Fn, and so on ad infinitum. So we find this chain of ideals like this, which does not become stationary because each time we choose an element which does not lie in what we had before. Which does not become stationary. And so that shows by contraposition that if we have this ascending chain condition, then every idea is fine. Okay, so maybe that's it for now. Next time I will show the Hilbert basis theorem, which is that the polynomial ring kx1 to xn is a Noetherian ring, and then we will draw some consequences. Okay, thank you. What?
Which example of the Noetherian ring are you going to prove?
What?
What example of Noetherian ring are you going to prove? You said something about you are going to prove.
No, I will show that kx1, the polynomial kx1 to xn is Noetherian.
Yeah.
That's the thing that I need. And then I draw some geometric consequences from that. Okay, I don't, not interested, yeah. Okay.
There are more examples of Noetherian rings?
Yeah, there are many Noetherian rings. I mean, even a power series ring is Noetherian. But something like a power series ring in infinitely many variables will not be Noetherian. As you can kind of imagine, these infinitely many variables give you the possibility to. But normally in algebraic geometry, one only deals with Noetherian rings, and everything is based on Noetherian rings because there are some terrible things that can happen otherwise. Okay. I don't know whether it's a good sign that it's blinking now. It was already blinking when before I pressed it.
It's the black one.
That's the